Good morning. I've been with this organization for many, many decades. I've never held a morning meeting, let alone on a Sunday. So, ladies and gentlemen, you are making history today. Welcome to the Hang Lung Mathematics Award talk that we started last year. Just a little history. In 1996-97, Sheng Tong Yao, the first Chinese mathematician and a good friend of, I know, Professor David Gross, and I'm sure, Ariel, you know him as well. He came to me and said, I'd like to start something, and would you agree to support me? And so we did. And so we started a thing called the Morningside Medal of Mathematics for Chinese mathematicians anywhere in the world. These are people who have achieved the highest standard of mathematics anywhere in the world if you're of Chinese descent. A few years later, he came back to me and said, and that was 21 years ago, 2004. He said, Ronnie, I have another idea. He's a very expensive guy, as we all know, David, and said, I'd like to start a high school mathematics research competition. I thought that was a great idea. So we supported him, and we started the Hang Lung Mathematics Award. Celebrating the 20th anniversary, we decided to do this public lecture. It's all free. Anybody can come from Hong Kong or anywhere. We have had some very interesting topics. Just to show you some of the topics we have done over the last year and a half. What is good research? We had Nancy Yip from Hong Kong UST and Zhang Xiang, the president of Hong Kong U, moderated by my brother, Dr. Gerald Chan, who's far smarter than his brother. In June, we started another one. We had another one called Good, Bad, and Beautiful of AI. And we had one of the world's top venture capitalists that invest in AI by the name of Antoine Blondeau, who lived once upon a time in Hong Kong. And he's now in Dubai. But anyway, together with Harry Shum, Professor Harry Shum, the chairman of the Council of Hong Kong UST, used to be the head of AI at Microsoft. So these are top people. And then we had a third one in August last year called From Lab to Life, How Science Rewrites the World. We had Professor Dennis Low, with whom I just had breakfast this morning, now the president of CUHK, Chinese University of Hong Kong, together with Professor David Ho, the AIDS person, so to speak. Many of you know him. The two of them spoke. And then in February this year, we had the Future of Universities, where Nancy Rothwell, a good friend of mine, just retired president of Manchester University, together with Lap Chi Choi of Hong Kong University previously. And then the last one we did in June this year was AI's Next Frontier, Insight from MIT. We had the Chancellor of MIT, Professor Eric Grimson, speaking here. We always try to find, if possible, young local professors to be the moderator. They are knowledgeable enough to ask smart questions, but hopefully they are not so technical that you and I don't understand, because this project, this talk is not meant for academicians. It's really for all of us. Some people ask me, why do you want to have this project? I said, well, three things. Number one, I want to inspire the young people of Hong Kong to pursue a career in science and technology. That's number one. Number two, to inform the Hong Kong general public so that we can have a society, a community that is more educated. It can only be good for us. And the third purpose of mine, I never told anybody. But since I saw a few wealthy people here, it is to lure other fellow business leaders to support, shall I say, science and basic research anywhere in the world, including Hong Kong. Well, before I introduce the three speakers, the two speakers with the moderator, I do want to pay tribute to a gentleman who used to come to our events regularly, and that is Professor Xian Yang. He is the first Nobel laureate of the Chinese race in 1957, also in physics, like Professor David Gross. And he is such a gentleman that have been very friendly to us here, for which we are very appreciative. Now that he's gone, I will tell a story about Professor Xian Yang. I know his first wife. she's a nice lady, but a little bit different, right, David? So Xian Yang, unbelievable the way Professor Yang treated his first wife, so nice. I'm so happy that every time I'm with them, my wife is not around. But sadly, she passed away, and then, of course, he remarried. And she, too, Wong Fan, became a very good friend of mine. And I called them when they used to live in Hong Kong periodically and say, why don't you come over to my home for dinner or my office for lunch, and my driver will pick them up and so forth. Or in Beijing, I would call them up as well. And whenever I host dinners inside, in particular the Forbidden City, where I spent 30 years rebuilding many, many buildings there, I would invite him and his wife Wong Fan to come and be my guests. Well, sadly, about a year ago, I hosted one of those events, and answering the phone was Wong Fan. Usually, when Wong Fan always answered the phone call, but usually I would hear a voice behind that says, "Honey, who is that?" This time, I did not see that. I did not hear that voice, and so I proceeded to invite Wong Fan and her husband, Professor Xian Yang, to have lunch with me inside of Forbidden City again. But sadly, Wong Fan told me that Professor Yang was in hospital. And she made it clear to me, being good friends, that it is impossible for me to see him again. So we all know that 7 days ago, Professor Xian Yang died, and he will be always remembered by all of us in the Chinese people, as well as in the scientific community anywhere. But let me say also that I think that Professor Yang was so fortunate to have found Wong Fan in his last days. In his last decades. In fact, when they had the honeymoon, it was in Boao, by the way. I was celebrating my mother's 85th birthday and found them there. We had to avoid them. We don't want to bother anyone. But I can say that their marriage has been really a lovely, lovely pair, that she really was very, very good to him to the very end. So anyway, just a word about Professor Xian Yang, who was so supportive of this program. But today, we're here in the land of the living. We're delighted that we have 2 Nobel laureates. I remember, David, Professor Gross, I remember the first time we met was 2006. Sheng Tong Yao, the founder of the Math Award with me here, asked me to host his friends inside of the Forbidden City. And who came? Professor David Gross, as well as Steve Hawking. I sure remember, David, you, Ching Tong, and I have to lift because all the doors in the Chinese buildings have a barrier, and so we have to carry Steve Hawking's wheelchair. That was almost 20 years ago. So good to see you still so healthy and good. Ariel is a professor a distinguished professor from my alma mater, University of Southern California. I don't know why every Nobel laureate from my school are chemists. George Olau is a chemist, you are a chemist, but we don't mind having more of them, so keep producing them, Mario. We're delighted that you are here with us today. So before I sit down, I just want to introduce the moderator. As I said, we try to find young talents in Hong Kong. So I found I like to think it's a perfect one because he has been a friend of mine since his college days. So with that, I will just tell a very short story to show you the quality of people in Hong Kong. In 2002, I taught a class at Hong Kong UST, the summer course. And you have to graduate in Hong Kong 99.6 percentile to jump a year and enter into university. And so I taught that class for several years in the summer. One of my first students is a fellow by the name of Joshua Lui. What happened to him? He eventually went to Columbia, got a PhD, went to MIT for postdoc. He's now a professor at UC Riverside, having obtained tenure. Well, I said, hey, Joshua, you're smart, huh? He said, no, I'm not smart. My classmate is smarter. His classmate is a fellow by the name of McKean Fai, we call him a Fai. And this guy eventually went to also Columbia, got a PhD, went to Cornell, and became a full professor at a very young age. And then what happened? Max Planck Institute in Germany set up a center just for him in order to get him there. And his wife, Shanjie, is also a physicist, and they set up another center for her in order to attract Afai to go to Max Planck. So I said, hey, Afai and Joshua used to come to my apartment and stay till 3, 4, 5 a.m. in the morning. And I say, hey, Afai, I heard you're very smart. He said, oh, no, I'm not smart. You ought to know my tutor. My tutor is far smarter. And who is the tutor? Well, I'll let you guess. He's a chair professor of Hong Kong UST now, and he will be our moderator today, Professor Vic Law. So, ladies and gentlemen, welcome to the stage, the Nobel laureate, Professor David Gross, Professor Ariel Washow, led by our Hong Kong's Professor Vic Law.
Good morning, everyone. So, thank you, Ronnie, for the introduction. I'm so embarrassed, and I was really just older than my friends by that time. So, and so I'm Vic Law from the Hong Kong University of Science and Technology. So, welcome to this fireside chat with two intellectual giants of our modern time. So, and Professor David Gross and Professor Ariel Washow. I have to say that I'm a physicist. So there's a holy grail in physics, which is to discover fundamental laws of our universe. That's the holy grail. And Professor David Gross did just that. So his Nobel-winning work is for the discovery of how quarks can bind together to form neutrons and protons in our universe and inside our body. So what he discovered basically is even very important to understand our own existence of human beings. So, and with my limited knowledge in chemistry, I also believe that there's a holy grail in chemistry. And that is to discover new molecular structures. If you find some useful molecules, and you probably will get a Nobel Prize. So, and it's our great honor to have Professor Ariel Washow with us. And his Nobel-winning work is for developing powerful computational tools to predict molecular structures and beyond. So now I think you understand why we have these two Nobel laureates sitting with us today, and the work because of the work that they had done. So, and with our two Nobel laureates here, so may I start with two big questions as the appetizers for our audience. And the first question is for Professor Gross. So, and are there new laws of physics waiting to be discovered nowadays? So are there modern experiments which we could not understand, which force us to explore new laws of physics? So, Professor Gross.
Sure. The search for new laws of physics or totally new phenomena that we don't understand is often driven by experiment. Right. Can also be driven by theory. So let me just give two examples that shape the current exploration at the most fundamental level. So one is experiment. Over 30 years ago, astronomers discovered that throughout the universe, there's a new kind of matter that no one had ever seen on Earth. It was discovered not because it radiates like stars, but because it pulls planets all mass attracts other mass. And in order to explain the motion of planets in our galaxy even, the motion of galaxies throughout the universe, it requires that most of the matter in the universe, 80% of the matter in the universe, is invisible to us, but must be there, and over the last 30 years has been mapped out in precision. We can't see this matter, but it pulls planets around in different orbits, and it bends light in a way that enables us to construct a map of this so-called dark matter, we can't see it, throughout the universe. And most of the matter in the universe is this dark matter. So for 30 years, we've been searching for other signals, properties of this dark matter. Can we produce it in the laboratory? With enough energy, you can produce anything. Can we detect it flowing through us? So far, no success. So this is a major challenge for fundamental physics and astrophysics and cosmology. Dark matter is essential to the structure of the universe. It dictates the history of the universe, and we don't know what it is. That's challenge number one. Experimenters have been working for 30 years and continue to do so, and theorists have been, therefore, encouraged to think of new forms, new ways of looking for this dark matter, new possibilities of what it's actually made out of. The enormous range of possibilities, major challenge to our understanding of the universe and to the structure of matter. Now we have another burning question, which is more theoretical in nature and is stimulated by our desire to understand the observable universe, but very hard to access directly by experiment. And that is the origin of the universe. The last 100 years we have been enormously successful through observation and theory to construct a map of almost the entire universe and its history, the last 13.5 billion years. But the question has now become a scientific question that can be probed both by experiment, observation, and theory. How did the universe begin? Now, as you must understand, that's a very deep and important question for all of us, and not one that physics has ever attempted to explain before or had the tools to do so. And yet, in the area of cosmology, astrophysics, and fundamental physics, it is at the forefront. And it undoubtedly will require, we already understand that, a deep conceptual change in our basic laws of quantum mechanics and general relativity, the dynamical structure of space and time. So those are two kinds of really deep questions that guide us in the future, now and for many years.
So in short, it's the dark matter and the origin of the universe. These are the two biggest problems.
There are many others.
Yeah. So do you have any candidates in mind about about dark matter, or at what energy scale that they would interact with ordinary matters?
I used to. So I would say 20 years ago, 30 years ago, there was an outstanding candidate, something called WIMPs, weakly interacting massive particles that were predicted by generalizations of our standard model of particle physics and seemed to be consistent with the known properties of dark matter, its abundance, and so on. And I would have bet, 20 years ago, I would have bet that by now, for sure, we would have discovered the nature of dark matter. We would have produced it at the Large Hadron Collider in CERN in Geneva, we would have seen signs of the annihilation of dark matter in space. But, so that didn't happen. This is often the case in science. You make predictions. You expect certain experiments to show new phenomena, and nature says, nope, you're wrong. Nature, by the way, never says you're right. It only says you're wrong. If it says, so far you're okay, many times you begin to gain confidence in your speculations. So nature has taught us for the last 20 years, all of the explanations we have looked for dark matter are wrong. Okay, we've learned something very important, and theorists are now in the business of exploring a vast range of possibilities, over 60 orders of magnitude in the size of what could be dark matter, from small black holes to a gas of axions, and so on. There are an enormous possibilities, and failure. This is something students always, what do you do when there's failure? You learn from that. So we learn from that failure that it must be something else that stimulates the imagination. And so currently there are literally dozens of very interesting ideas and new experiments, new observations that can be carried out in the search to understand what is the dark matter that fills the universe.
Thank you, Professor Gross. And for Professor Warschau. Oh, maybe you take mine first. So, Professor Warschau, so as a chemist, so what is the biggest mystery in chemistry nowadays? This is another appetizer for the audience.
Okay,
That's
first
a big
of all,
question.
my field was not discovering structure of molecule, but actually figuring out how they work, how biological molecules work.
Right.
And one of the biggest mystery, since chemistry is everything, is how the brain actually work, the chemistry and the biology of the brain, trying to figure out what really happening there. There are great experimental advantage and also biological advantage in finding structures, but there are open questions. Practically, you want to be able to understand and to cure Alzheimer's, but more importantly, you want to understand how emotions are working, where the memory is stored, what is the chemistry of this process. And it probably will be solved in, again, the next 20 years, so it's a very, very nice challenge. And I would put this as the holy grail of chemistry. Now, there are a lot of practical questions, like you want to be able to dissolve plastic.
Right.
These are practical, I mean, you need some enzymes to do it. So you want to be able to generate drugs for any possible disease and to do it effectively. So again, it's less exciting than figuring out the origin of the universe, but figuring out how the brain works is, and as a footnote, when I start to work on ATPase, which is molecular motor, I try to look for some YouTube, and the first ones that I found say, look, this ATPase is so complicated, so I keep looking. So there is no chance that it was created by evolution. It must be done by God. And I decided just to understand how it worked, but not how it was form. So the question of the origin of life is also an interesting challenge.
I see. Well, these are very big questions. So may I have one follow-up question then? You know, as the Professor David Gross talked about, when physicists search for dark matter, right? I think Professor David Gross' approach is start from the standard model, something you're familiar with. So you have a starting point to predict this massive weakly interacting particles. So, and in chemistry, Professor Washow, you just talked about this very important questions of how the brain works, what's the origin of life. But as a chemist, so what's your starting point to start to attack this problem? What's your entry point?
The starting point is knowing that it is done by molecules. Now, the action of molecules described by forces which are not puzzle at all. I mean, you could use quantum mechanics, you could use classical mechanics. On the molecular level, there are no fundamental questions. The question is the complexity, how series of large molecules talk with each other. So the way I attack problem, I look on the structure of the main molecules, try to understand how they work, and then I try to see how they do what they're doing. So it's not, I don't have to invent new physics, but when I try to understand molecular motor, it's extremely small motor. I know that I should be able to describe it, but I want to describe it on the same level that we understand, let's say, water wheel or something.
Right.
So you want to reach the physical description, and sometimes it's very, very complex. So the complexity is your enemy that you want to understand.
Right. Yeah, so I think that the lesson to the young people is that you identify some big problems and you find the entry point to it. Right? So the next question is about quantum mechanics and curiosity-driven research. So actually this year is declared by the United Nations as the year of quantum science and technology. So, and the reason is that 100 years ago, quantum mechanics was formulated. And you know, many of our audience are probably too young, but actually if you look back at the history, people lived quite a good life 100 years ago. You may not know that they had Mercedes. They know mechanics really well. They have Boeing. They have AT&T. So they have telegraphs. They have early versions of televisions. So you know, people live quite a good life in some sense. And you probably heard about Thomas Edison and Nikola Tesla. They were fighting against each other to provide electricity to people. So that was a time, you know, just like right now, people are quite satisfied with their lives. But there was a small group of people who were not satisfied with their life. They tried to answer some curious questions like why atoms are stable. You know, why the hot objects emit lights in certain ways. You know, these are totally irrelevant questions to our daily lives. So and then to answer these questions, quantum mechanics was formulated. And once you understand quantum mechanics is you know, something that the law basically in the atomic world. So once you understand the atoms, you put atoms together, so you have molecules. You understand molecules, and then you put a lot of molecules together, you have crystals, and then you have semiconductors. That really started the whole information age that we are in right now. So that really tells you the power of you know, fundamental research and curiosity-driven research. So my question to our two laureates is that, you know, now we have a much better understanding of the world. So should we be satisfied? Should we still do curiosity-driven fundamental research? So these are the questions for our two laureates. So.
Well, okay, if that's the answer is easy, obviously. Yes. So, talking about your historical description is not completely correct. There were many properties of light that were not understood.
Right.
For the quantum properties that
Right.
led to Planck's
Right.
introduction of the beginning of quantum mechanics.
Right.
Now, that wasn't particularly important for the technology of the 19th century,
Right.
but it's the quantum mechanical properties of life that produced the laser,
Right.
for example,
Right.
and much of modern technology. Not to speak of the quantum mechanics that allows us to understand atoms and molecules and chemistry, but the quantum mechanics of solids that, as
Right.
you said, semiconductors that led to modern computers, and now so in my opinion, at any point in history, we think, say, low energy physics, the physics of atoms and molecules and ordinary solids and fluids, we kind of understand the basic laws.
Right.
But in my opinion, we're still just at the beginning of the exploration and understanding of the quantum world. It's very young. Quantum mechanics is only 100 years old.
Right.
That's not much more than a human lifetime. The exploration of quantum mechanical phenomena, the quantum world, which is so complicated, so new conceptually, is just beginning, I believe. And will go on for a few hundred years. Even at the level of ordinary quantum non-relativistic, low energy by my standards
Right.
physics. And that's obviously taking off in a big way nowadays
right.
with quantum,
Yes.
enormous investments in new ideas that have come out of our growing understanding of quantum effects, many body systems,
Right.
new kinds of material,
Right.
quantum computers,
Yes.
and most of the advances have not yet been even dreamed of.
Mm.
So somebody can come back 100 years and see your remarks and say, oh my God, they had no idea what is
Right.
actually
Right.
possible.
Right. I'm doing fundamental research, by the way.
I know. But
Yeah.
yeah. So
I fully agree with you.
not to speak of the areas that have been driven mostly by curiosity,
Yeah.
which still one cannot yet imagine the imagination. So the historical evidence for the importance of fundamental research is, as you stated, is clear, but I think it goes way beyond that
Mm-hmm.
and is enormously exciting.
Thank you. Thank you.
Okay, so
Professor
many
Washout.
years ago, one physicist says that after the Schrödinger equation,
Right.
chemistry is solved, there is nothing to do. Who was it?
That was Paul Dirac.
Paul Dirac.
Paul Dirac, he was 32 years old. He just won the Nobel Prize. He had predicted the positron. He was, arrogantly made
So
a statement like that, which he shouldn't have. It's kind of, he didn't really mean what you're attributing to him, that he really believed that chemistry was solved. But what he meant was that, of course, that the basic laws of relativistic quantum mechanics
Right.
are at some reductionist level the basis for all the physical sciences.
Right.
And, after 100 years, he hasn't been proven wrong.
Right.
yes,
Right.
But he obviously knew that, okay, he was unable to use those basic laws, the Dirac equation, quantum
Right.
mechanics, to understand even simple chemical
Right.
systems.
Right.
okay.
He knew that.
So in the 80s, we had a meeting in Amsterdam, and we bet when the protein folding would be solved. And we say we'll have a dinner when So some people say 10 years and so on. A lot of the people who propose the bet are not with us anymore, but it was kind of solved by AlphaFold.
Right, right. That's a
Now,
protein folding problem.
On
right.
related things, we try to form a group to study how the cell work,
The cell.
and the organizer posed the question, when we will be able to simulate the cell on a molecular level. And some people say 2 years. I instantly wrote 70 years, and I might be also wrong.
70.
Yes. And so there is a lot still to understand, and a lot of them is either you could call it curiosity or just want to be the first to figure it out. So curiosity driven is a kind of a key for progress in science.
So I think Professor David Gross must be very familiar with the statement of Phil Anderson, right? So more is different. So even though the fundamental laws of physics, even though it's known like the Dirac equation, but when you have more particles together, there's many boundary problems, including the chemistry problems, are extremely complex, which is very useful, but it's difficult to understand. These are still some of the hardest problems of modern science right now, right?
Sure. One of the recent Nobel Prizes was given, in a sense, for study of complex systems.
Right.
Parisi and they're very hard, of course, and
Right.
fascinatingly interesting. They're also deeply related to neural networks and
Right.
to AI and large language models. The most interesting aspect of science in general is that the border between fundamental and applied is often very interconnected, so that some of the ideas that we are learning to understand the laws of fundamental laws in different situations are often connected to new insights into how to apply these to other different complicated systems.
Right.
The unity of physics across fundamental to to complex systems is sometimes remarkable and incredibly important. So more is different. Well, it's kind of obvious.
Right.
What's new? But what Phil was emphasizing was that although there are really no rational scientist nowadays, but has a challenge to the reductionist structure of nature that we have discovered over the last few hundred years. But it's obvious that, and more we understand that very interesting new effects arise in our effective descriptions at scales where we're only interested in the average phenomena or in larger distances. And but these emergent phenomena that are not inconsistent with their description in terms of fundamental laws.
No, they're not, right.
But have a kind of existence of their own, are extraordinarily powerful in every area of physics.
Right.
And often in many different areas, which are apparently quite different.
Right. So. Thank you. Actually, that's also my job, to study these emerging phenomena in many body problems. Yeah. So, my third question is about the social impact of fundamental research nowadays. So, actually, this year, the Nobel Prize in Chemistry was given to the discovery of a meta-organic framework, and which is you have some carbon molecules, nitrogen molecules forming cages to host these metal atoms, metallic molecules. So, and then this year's Physics Nobel Prize, given earlier this month, went to the experimental verification of some quantum phenomena in macroscopic objects, meaning sizable, large objects. So as we mentioned, quantum mechanics is supposed to show to be important at atomic level. But this year's Physics Nobel Prize showed that they are also important in macroscopic, in large systems. So, but I have to say that these discoveries, it seems to me that the societal impact are not so big at this stage, and at least not now, right? So for our two laureates, do you believe that the fundamental research is being...
No.
Right, okay.
Yeah, totally.
So I'm wrong. You see, I learned from my mistakes, so please.
Well, I mean, I'll start with the physics prize, which was won by two of my colleagues in Santa Barbara.
Right.
Very pleasant. That was originally for trying to test quantum mechanics. So, as you know, quantum phenomena, if you apply quantum mechanics to big objects like us, can raise all sorts of strange possibilities. Schrodinger's cat is the most famous example. Could you imagine a cat in a superposition, a quantum mechanical superposition of being dead and alive?
Right.
Macroscopic objects in pure quantum states rapidly decohere, lose their quantum nature in interacting with the environment.
Right.
So theorists wondered whether, if you tried to be very careful and construct a big macroscopic system like a cat, quantum mechanics would fail, because it was crazy to imagine
Right.
a cat both dead and alive until you actually measure it. And so this group at Berkeley 40 years ago tried to use the Josephson effect to see if you could tunnel, sort of from one state to another through a barrier with a macroscopic number of electrons, hundreds of thousands, millions, and succeeded in testing quantum mechanics, in a sense, in creating artificial atoms, which are on a chip, which are, big, but have quantized energy levels. Amazing, beautiful experiment.
Right.
Totally driven by curiosity.
Yes.
Is quantum mechanics applicable to macroscopic effects? With no idea of what it's good for or anything. But it was the beginning. I mean, of course, the result was quantum mechanics works.
Right.
Don't worry. Shut up and calculate. But but that stimulated experimentalists to try to develop these macroscopic quantum systems. That's just a challenge. Can you do it? And but that development of experimental and technological development was necessary to try to imagine making use of these macroscopic or semi-macroscopic quantum coherent states of matter to imagine doing quantum computing, for example, or quantum sensors. Such devices can be very sensitive to be used to measure magnetic fields, for example, and things like that.
Right.
Enormously amazing technological, so far mostly possibilities. And now, of course, it's not yet realized. It will be, however.
Right.
But literally hundreds of billions of dollars are being invested by very smart companies,
like Google,
to Google, Microsoft, IBM,
Microsoft,
the U.S. government, the European government, I'm sure China as well. So this is what happens in science. You start with just playing around in the lab and trying to test fundamental ideas. And
so basically they started the so-called the second revolution of quantum mechanics. You believe that? So we start to be able to control this quantum states in macroscopic objects, right? So this is the beginning of the quantum computation.
Right.
Yeah.
Well, yeah.
So And I was wrong, okay, about chemistry as well. So
Being twice wrong is not so bad. So,
oh,
Omar Yagi, for example, designed these huge cavities,
right.
which, by the way, now is using AI to decide which one to do.
Hmm.
And they are able to capture CO2, to capture hydrogen, so
Right.
they are extremely useful. Probably they must have several companies which invested this. So it's not.
Oh, I see.
It's not. I mean, at first it was a show off. Look how
Uh-huh.
what I could do, but it became very, very practical and important. I mean,
I see.
the surface area of this cavity is
Mm-hmm.
enormous,
Hmm.
and people are using it.
Oh, I see. So actually, both of these discoveries, both for this year's Nobel Prize in Physics and Chemistry, and they are actually emerging to be very important technologically,
Yes.
right?
I mean, they're great example. I am not sure why you said they're not. Because
Maybe to trick us.
they're almost pin-up examples
Right.
of curiosity-driven research
Right.
leading to immense technology.
Right, right. So this is great for our students here. So, and my next question is probably also, I think the audience is waiting for this, which is about the era of AI.
Oh.
So on the other hand, last year's Nobel Prize was, given the physics Nobel Prize was for the development of the artificial neural network, as Professor Gross just mentioned. And in chemistry, it was given to Google DeepMind scientists for AlphaFold, which is for the prediction of protein folding. So AI is really becoming so powerful. Do you believe that we are at the beginning of the AI era?
I think there's an enormous amount of hype. I was going to ask Ronnie, how do you sell AI short? But, well, so last year when the Nobel Prize was given to John Hopfield, who was a colleague of mine at Princeton for many years, I enormously admire, a lot of my friends in physics were shocked, actually, condensed matter.
Right. I was shocked at the beginning as well.
And I thought it was a wonderful prize.
Yes.
It was an example of how physicists can often have enormous impact on fields outside traditional physics. And Hopfield developed this neural network, of course, model of memory because he was interested in the brain. And as Ariel talked before, one major problem is, among the rest, is how we store information in the brain. And he was the condensed matter theorist, was well acquainted with systems, complex, frustrated, disordered systems in condensed matter, spin glasses, and it seemed like a kind of interesting model which one might apply to construct a model of neuronic memory, neural network in the brain, which had enormous impact on the field, neuroscience, and memory, models of memory and then of computing. And Hinton was not a physicist, but a computer scientist, developed a similar physical model of how such dynamical neural network could work based on statistical mechanics, thermodynamics, the Boltzmann machine, I think it was. Anyway, so these ideas from physics had an enormous impact, and many physicists have been involved in developing neural nets. And eventually, simply Moore's law and the size turned out to reveal that they work incredibly well beyond a certain size. How they really work, nobody understands. I mean, that's clear. I'm not that impressed by the AI as an intelligent machine. but it has certain great capabilities. Give it enough data, it can make reasonable conjectures as to what a good answer is. Often it lies and is wrong, has no way of verifying. It certainly is not intelligent in the sense that everyone in this room is. And I doubt whether it will replace us or destroy us. But it's certainly like the computer, the slide rule was, the computer was, and now these neural net, large language models, and what else will come, have enormous power. I mean, I have seen in my lifetime how modern computers, which have increased in power over my life by roughly 10 to the 12th, a trillion times, have changed the way we do physics and mathematics and every science. We can, even just at the level of experimental physics, doing experiments in the lab, big science, it would be impossible with the computers of 30, 40 years ago.
Right.
So the ability to improve our calculational ability over the history of science, from logarithmic tables to the slide rule to modern computers to AI, is one of the computational and tools that we have invented and will enable us to increase our power. Wonderful, but the hype is even more extraordinary.
So it's a very powerful tool, but not as smart as the audience here. So, Professor Warshall, so I believe AI is a very powerful tool for, actually probably the AlphaFold also built on your work as well. So what's your opinion on this?
Okay, in 1975 we already were able to model protein folding, but so AlphaFold does not predict the folding process. It's just predicts the folded structure.
Right.
And essentially, when we wrote our folding model, my boss, Schneur Olivson, say, "Oh, it's not interesting at all. It's like asking how a leaf falls from a tree." I don't know. I don't think he was right. But actually, I regret to say that I'm using AI. I started to use it 5 years ago. Essentially, I would even say that my PhD, which was developing a force field, was, I could have called it AI, because I fit parameters to observable, but nobody knew the name there. Now, it's very hard to fight AI. It gives you good predictions. It's extremely popular, so students want to do it. So my only point to you is that be careful. Try to still stick to physical studies, because otherwise you will be the slave of the AI. You want to understand what does it tell you, and if you just operate the machine, it's not a good idea, because AI does not tell you the reason, at least at present. It tells you what is the result based on many predictions. Essentially, I have a nice story to say that about 20, 30 years ago, I was in a conference, and some postdoc talk on a model called What If, which was kind of AI, and I really say that this is extremely stupid, because obviously, if you have a protein that is similar to trypsin, you could predict the rate constant that this protein works just by saying that it is similar to that of trypsin, and you will be doing much better than I'm doing with my extremely ambitious calculation. So you will know the result, but you will have no clue. So he was extremely offended, and essentially I realized that this was one of the first AI model.
Right.
But later I realized, again, I'm happy that I said it, but later I realized that, let's say, if you have mutations and you learn from similarity, it is not so bad. You don't understand why it is happening.
Right. Right.
But you have a powerful tool, and clearly in medicine, you could diagnose diseases by looking at different factors if you know a lot of them. And my friend who used to invest in gold 2 years ago started to invest in AI.
So yeah, I actually agree. So AI give you a lot of results, and you don't know if it's right or wrong. So I think the young people really, you have to learn a lot. You need to have the domain knowledge to know if the result is right or wrong, good or bad. Right? You need to have the judgment, right? So my fifth question, actually, we talk a lot about Nobel Prizes, and also Ronnie at the beginning mentioned about C.N. Yang, and we lost him a week ago. So he's the most important Chinese laureate, I may say, and he's a role model for generations of Chinese physicists, and he's more than a physicist to many. So, and given the deep connection between your work on quark-quark interactions and the Yang-Mills theory, I think Professor Gross is one of the best person in the world to talk about Professor C.N. Yang's achievement. So, could you please share with us Professor C.N. Yang's legacy from your perspective?
Well, I knew Frank Yang, as we called him in the United States, for over 50 years. But he was, he was, and by the way, his colleague and T.D. Lee as well. I knew them both. I was at Princeton. Yang and Lee both had been at Princeton and would come and visit very often. And Yang, of course, is famous for, Yang and Lee are famous for their suggestion that parity might be violated, reflection symmetry of nature might be violated in the weak nuclear force. They suggested how to test that, and that was discovered rapidly, and they, at a very young age, won the Nobel Prize, the first Chinese Nobel Prize. And they were very important figures in my field. Yang also had developed with Mills a beautiful generalization of electromagnetism, Maxwell's theory of electricity and magnetism, for cases where there is more than one kind of charge, not just the electric charge in the case of electricity, but more than 2 charges, 3 charges. And those theories turned out to be extremely important in my research and in the development of the basic standard model of particle physics. They are the forces, the way of describing the nuclear forces, the weak nuclear force with 2 charges and the strong nuclear force, which is my field, with 3 charges. So Yang was also an incredibly good mathematical physicist. He was did originally with T.D. Lee, but also by himself, some beautiful work in the statistical mechanics of many-body systems. And they were both major figures in my field, and I had quarrels with Yang over the years. Some of them were quite visible and in the Chinese press over the plans of China in fundamental science. At some point, Yang had decided that particle physics, which was his original area of expertise, Yang-Mills theory,
Right.
so on, was no longer interesting to him, at least, and advised young Chinese to do condensed matter
Right.
theory, like our moderator here. TD, on the other hand, was quite the opposite, and he was a great promoter of particle physics in China, responsible for the PEPS collider in Beijing. He initiated the program that brought Chinese students after the Cultural Revolution to the West. So I interacted often with both of them on different levels, and they unfortunately did not disagree on a personal level and on how China should develop in science. I found this very unfortunate since I admired them both very much, and they were very different, which is maybe why they quarreled. But they were both very special and great scientists. And T.D. Lee died a few years ago,
Right.
and Yang, of course, died last week. And it's sad to see such giants disappear.
So what was your argument with CN Yang about the building of the accelerator in China?
Yes, he was very much against it,
Right.
for no good reason.
I'm sorry to hear that.
But, everyone has different opinions, and I've had some very interesting conversations with him.
Yeah. So, Professor Warshau, so is any of your work related to Professor CN Yang's?
Of course not, of course not, but I read about Lee and Yang in Israeli newspaper and did not understand anything. However, the son of Yang was assistant professor at USC, organic chemistry. He did not get tenure, which is not the only one, but at least I voted to keep him.
That's very important.
So this is, but I never understood. Maybe one day you will explain it to me. It was called Torat HaZugiyut in Hebrew.
You definitely understand chirality.
Yes.
So Li and Yang essentially suggested that nature at its fundamental level was chiral. And that's in fact true.
Okay, you see,
Yeah,
very short explanation. As they say, you explain all the Bible on 1 foot. Yes.
So, well, that's our two laureates are really inspiring. So, and maybe due to time constraint, So I just would like to ask, this time for Q&A. So, before that, would you like to give some advice to our young people and our audience here? Because nowadays, science and engineering are so important and so powerful. And also we are at the age of the rising of AI. So not everyone is so good at science and engineering, right? Some of them are good. And so how can our young people or our audience, prepare for the rising of AI and in this, when science and engineering are so important, and how can we prepare for that? What kind of skills, what kind of mindsets should they acquire?
Okay, so it's very, very tempting to just use ChatGPT and to not to think what is the origin of everything. So the preparation must be in learning mathematics and physics, some chemistry, learning the fundamental language of science, because this tool is extremely important, and later you could do whatever you like. But the older you are, the harder it is to study physics, for example. Essentially, I noticed that every part, I was sick when they taught complex numbers, and I never fully understood it. I was afraid to do integrals in complex number only because I did not attend the class at that time. This is, by the way, a true story. So please study the fundamentals.
Thank you, Professor Washout. Professor Gross.
Well, my advice is somewhat different. Different aspect of advice, which, so I imagine the young people here, students here, are somewhat interested in science. But I would just, there are many other possibilities. You might go into business, to finance, to this, that, computer science. Let me just advocate a life in science. It's just a great life.
To some of us.
Especially when you win a Nobel Prize.
No, but that's not so important. The important thing is that if you are interested and curious about the world, then a life in science is fantastic. You are paid to follow your curiosity, your interest, and to do every day. It's not easy, but do what you enjoy doing. Also, science is an international enterprise. If you become a scientist in some field, you will be able to travel the world and meet people who have the same interests as you, same language as you, cooperate with them, work with them. It's fantastic. And you will be dealing with the world, the natural world, which, yes, and its values, its beauty. So, personally, I can't imagine a more enjoyable life. It's true that if you're successful, you get rewards, but that's true in every field. Right. But actually, when you're doing science and discovering new things and new phenomena and new ways of understanding nature, that kind of satisfaction you will get from that. And working with colleagues around the world is not, I think, available in many other areas of human activity. So it's worth making the effort if you love to do that kind of thing, if you're curious and you enjoy doing it. You could not imagine a better life than that of a scientist.
So, thank you for the so inspiring sharings of our two laureates. So, may I invite questions from the audience? Okay, wow. Maybe the student first. Okay, so Ronnie told me that students should go first.
I have a question for Professor Warshall. Back to you said one of the fun, the questions in chemistry is how does the chemistry of the brain work? Do you think there's something special in how the human brain perceives time, and can it be altered through some kind of drugs?
Essentially, this part is well understood. We know the structure of different GPCR. I'm even working on it. You know how the drug interact with them. So the initial part of sending the signal is understood on a physical level. What it does later in the brain is the puzzle. So, for example, for depression, there are maybe 50 different receptors. You don't know which one is important. But for a specific one, like the heroin receptor and so on, you know the structure and you know the beginning. It's just what it does in the brain is unclear.
Thank you.
So the gentleman at the back, right? The two, right? In blue, yes, in blue, and then in red, yeah, the two gentlemen over there.
Thank you very much, Professors Gross, Warshaw, and Law. It's a true privilege to have you here in Hong Kong. I'm an AI ethicist based at the University of Hong Kong, and I'd like to ask you a question, unsurprisingly, about ethics. In the age of AI, to what extent do you think scientists ought to develop a deeper and more robust understanding of ethical and normative questions, going back to the classics like Aristotle or Confucius, to help themselves understand how to navigate the challenges brought about by AI? Thank you very much.
Essentially, 2 years ago, I was in a conference in Sweden, which was dedicated to the question of how AI will get a Nobel Prize. And half of the meeting were about the ethics of AI. And I must admit that me and my colleague left this meeting. So I really, no, I don't put down. I was hoping to hear from people from MIT more about AI than about the ethics of it. But it's like any question about scientific ethics, there are always sides, like the invention of Fritz Haber, who invented way to do ammonia, and on one hand it helped to grow crop, on the other hand it led to production of dynamite. So there is a question in any scientific discovery how to control the development, and I'm not sure what is the direction. I mean, you clearly have to block the bad direction, but it does not prevent people from inventing things with a dual use.
So maybe the gentleman in red. Yeah.
Professors Gross, Warshaw, and Law. I'm incredibly heartened by your talks. I come from a math and condensed matter theory, materials theory background. But when I started my PhD, I kind of pivoted to AI, not really of my own volition, but because of funding. And so now I work, I'm a researcher, I work at the intersection of AI, education, and neuroscience, so a bit of, and my question is, how do we get your message? Because I am in complete agreement, right, in the value, the importance of curiosity-driven, fundamental science. But it seems more and more people want, immediate results. People want application. The world is moving faster and faster. How do we advocate to governments, to, a lot of AI work now is done in industry. How do we, to investors, that this is important? Because I really need to know. Thank you.
Well, it's never easy to convince industry or governments about making long-term investments of any kind, especially in areas where you can't predict the results. You just tell them that they will come, for sure. But that's a problem. I don't think of AI at the moment, as far as I can tell. You just say the word AI and you'll get people to give you money. So what's your problem?
You got the funding.
I want to expand on this suggestion. Essentially, one way is to get the money for something which is popular, but on the side to do the research that you like to do. This is.
So I think now you understand why Professor David Gross said that life in science is so good. That's what we do, right? Okay. So the lady, yes. Yeah, on the second row. Yeah.
Thank you, both professors. Quite a treat to listen to both of you. In addition to the ultimate mystery of origin of universe and origin of life, there's also ultimate multidisciplinary mystery, which is the origin of consciousness. So do you think the scientific evidence has arrived to the point for us to challenge if consciousness is refined in our physical brain? If not, what else needs to happen for us to challenge that assumption? Thank you.
So you know that consciousness is not very well defined. Alan Turing came up with a test, the Turing test. Somebody told me that AI has already, or one of the versions, has already passed the Turing test, which just goes to show that that's not a good definition of consciousness. And so it's a very ill-defined term, in my opinion. And it's clearly a very difficult problem. C. elegans, this one of the simplest biological worms, very small, has its complete neuronal system mapped out. We know every neuron in the worm and every connection, and still can't understand how it works. So it's a very difficult problem. Don't understand, by the way, how AI works either. These large language models come up with answers based on all the data on the internet.
Right.
And nobody truly understands what, as Ariel was saying, the principles behind this are. Consciousness evolved over 5 billion years. It's not easy. And it's one of the great challenges of science. But it might take 100 years to understand that. None of these deep questions like the origin of the universe or nature of consciousness are goals, not challenges that are going to be immediately answered. Perhaps there will be breakthroughs, always possible. Often happens, but you can't expect it.
So currently, all these AI models are built from classical computers. So in principle, they are all deterministic. So, but human beings, our brains are...
They use stochastic elements as well.
No,
when you want to...
They give you different answers, so they are not deterministic.
They're always stochastic. If you're in a complicated landscape and you want to find a stable state,
right,
heating it up,
right,
and so there's always stochastic elements, but classically stochastic.
Right.
Quantum computers is a totally different thing than AI. That enables one to solve problems that AI is totally incapable of doing. AI is an ordinary computer.
Right. So I think my question is just that. So in your view, quantum elements in AI, not quantum computing. So it's not so important, right?
There are no quantum elements. There's stochastic elements. You
nowadays
throw a dice every once in a while.
Right. So maybe we can take one more question. Yes, the gentleman.
Sorry. Thank you for advocating for science. My question is, how do you feel about what we're seeing as the attack on science, primarily as we're seeing coming in the United States? How concerned are you? Maybe what are the origins of this? And maybe does this create opportunities in Europe and China and the rest of the world to take more leadership? Thank you.
Okay, the anti-Trump advocate will tell you.
Oh, it's horrifying what's happening. Yeah, it's hard to understand. Anti-science, fake news. What's happening in the United States is truly mind-boggling. We are destroying our public health system, promoting crazy ideas about vaccination. My stepdaughter is a pediatrician, hospitalist in the Bay Area, and she is just horrified at the possibilities. Every once in a while, there's a rich kid from Marin County whose parents believe that vaccines create autism and have not vaccinated their children, and someone infected with measles comes into the pediatric ward in the hospital, and they have to evacuate the whole floor because this one person with measles. The number of unvaccinated children or children who are immune compromised with pediatric oncology, cancer, are enormously susceptible. And the devastation of just one stupid child who is not vaccinated because of the is enormous. And we're now doing that widespread throughout the United States. So it's part of a whole culture of fake information, some of it politically motivated, some of it just crazy, in a wide variety of areas. Then there's, of course, the recent attack on science and scientific institutions in the United States, which is hard for me to understand where this comes from, except for trying to destroy the university system that we have in the United States, and that's political motivation. But it's incredibly dangerous. I think you asked whether this is an opportunity for Europe. Absolutely. My European colleagues are trying to take advantage of this, to lure American scientists to Europe. Yeah. China as well is doing that. Right. For many of our Chinese colleagues, it's awful. That's the anti-Trump message.
Professor Washout, do you have something to say?
Okay, no, I won't say it here.
Okay.
But I admit that this part is problematic.
Okay. So,
sorry, I just have one more question from the back. My name's Connor Mycroft. I'm a reporter with the South China Morning Post newspaper here in Hong Kong. Thank you both for your speech or talk today. It was very illuminating. I'm sure everyone in the room learned a lot. I just wanted to ask really quick, from my understanding, both of you have been to Hong Kong before, if I'm not mistaken. You're not unfamiliar with the city. You know, Hong Kong is usually looked at as an international financial hub rather than anything else, or primarily that. And increasingly, it's trying to become known more for scientific research, innovation, artificial intelligence, much of what was discussed today. And I was just hoping you could quickly share your thoughts on that development in the city, and if you have any advice for Hong Kong writ large or its universities on how to achieve that goal. Thank you.
thank you.
Okay, I've been in Hong Kong a lot. Essentially, I am affiliated with the Chinese University of Hong Kong in Shenzhen. And I think that Hong Kong is doing quite well scientifically, and probably it will continue to do so. So I think there are several universities here which are quite top-rated, and just continue doing what you do. Maybe you could lure some anti-Trump scientists to China.
Not necessarily a question of being anti-Trump, just being Chinese is enough.
No.
Anyway, no, I think I've been coming to Hong Kong for many years, I'm not sure the development you're talking about is obviously driven by many other considerations, but I've always thought that Hong Kong had more possibilities in the scientific area. It has a very good educational system and very good, smart young people. And so from a point of view of a scientist, I'm happy to see more emphasis on science and technology than on business. So it's a good development from my point of view, although I'm not sure exactly what the economic reasons are that have led to this. But it's definitely lots of opportunity in the direction that Hong Kong seems to be moving.
So thank you very much, and because of the time, and then we end the Q&A section here. And let's thank the two laureates again for their truly inspiring sharing. And I would like to pass the stage to Ronnie.
Thank you. The reason I mentioned my 3 students at the Hong Kong University is to show you that Hong Kong does have really very potential young people that if they are given to science and technology, I think they can really be world-class in their future. Since this thing is the Hang Lung Math Award, I want to go back to something that my co-founder of it, Professor Sheng Tong Yao, said to me many decades ago. He asked me, he said, where is the best place to find the next Nobel laureate? And I said, I don't know. He said, the best place to look is the laboratory of the existing laureates. As David Gross mentioned, that his colleagues at Santa Barbara, 2 of them have just won. I remember, David, that your student, actually, Frank Wilczek, actually received the Nobel Prize together with you. I think he was your first PhD student. And then another student of yours, who is also a friend of mine, who received an honorary doctorate at USC, is Ed Witten, who is the first physicist to receive the Fields Medal, which is in mathematics. And so I think that to be able to hear and learn from the best in the world is very, very important. And the last thing I want to say to the student is this. Sheng Tong told me another thing. Professor Yao said, your brain peak out when you are 32, 33. Well, he received I think he received the Fields Medal when he was 33. And it does peak out. Later in life, you use not just your brain power, but also experience to catapult you further. So start young. I'm so delighted that so many of the students are here. They are our future. Let's hope that some of them will one day, you don't have to receive a Nobel Prize. You can still have a very good life in science. But who knows, maybe one of these days, one of you will say, I listened to those 2 Nobel laureates, and today I become one of them. Ladies and gentlemen, let's have one more round of applause for the 2 Nobel laureates and to our moderator, Vic Law.